Well, today we're going to talk a little bit more about these big language models, of course, which are all the rage, and specifically we're going to talk about how they do this reinforcement learning from human feedback, which is one of kind of the secret sauce, if you will, for the big language models and things like that. Um, what we'll do is, as you can see, it's kind of the underlying technology used to train our models that we use in ChatGPT, Bard, and things like that. As part of the GDE program, I've been using it quite a bit in the Bard side, and their tools are pretty much the same as what you have in ChatGPT. Um, but anyway, what we're going to do this is to watch this video from a group, Deep Learning AI, their workshops. And this is kind of a pitch video, if you will, for their workshop. So it's not the actual workshop itself. That is a for fee type thing. But it is very good. So, if you're interested in learning more, I wouldn't hesitate to spend. I don't know what it costs, but it seems like they really understand what they're going to do. There's actually two parts of it. One is more hands-on, or excuse me, a discussion about what RLHF works is and how it works, and that's what we're going to focus on. We could go and do the code, but I think if we did, we'd run way, way over. So for right now, I'm not going to commit to doing that unless you guys really, really want to do that. Everybody cool with that? Okay.
Sounds good.
Standard stuff here for anybody that's new or hasn't been here a while. And we're just a real small group tonight, so this is a good chance here. If I say something or something goes on the screen and you don't understand, just say stop and let's discuss it right then, because everything builds on top of each other. So, you can kind of get behind and things like that. And if we don't finish tonight, we don't finish tonight. We just slip or whatever. So don't worry about it. We're small enough that we can really, customize it here to ensure everybody has a great experience. So let's do that. Second, I'm gonna do a quick pitch for the channel since I spent some time doing that. This is, we have our West Coast ML channel here, but we are recording all these meetups and things like that, and they appear up on our channel. So if you go to the West Coast ML channel on YouTube, you'll find this. This is one I think Roger did, I don't know, a couple of weeks ago or something like that. And I've been out with COVID, so I just got around to putting it up there. But this is kind of what they all sort of look like there. Okay.
To one of the topics we're covering, that's RLHF. Also, here's a bit.ly link, GLLM, if you don't want to type the full link, but I think we're also posting it here in the chat window. All right, let's jump into today's topic. So in the course, we're not only covering reinforcement learning, we're really kind of looking at generative AI from an end-to-end project lifecycle. And you can see here, we're starting with defining the problem, talking about the use cases, how you can choose the right model. And then here in the middle, we're diving into the how to adapt and align your model project phase. And this includes a couple of different things, right? From just using prompt engineering to kind of guide the model towards the right outputs. And then a big section of the course will focus on the fine-tuning. So how can you customize the model with your data for your specific use case? And fine-tuning, as I said, is about customizing the model, also helping it to understand human language, the prompts, and understanding tasks better, also responding in a little bit more natural sounding language potentially. But there's a problem with that, right? Human language, as we know, sometimes has different tone. Sometimes the models pick up language if it's trained on data from the internet that we don't want to have it replicate to our users. And there's a couple of examples, not just the tone and models behaving badly, but also, for example, one of the non-official evaluation criteria, just a personal one that I do. If I'm working with a new model, I'll try to tell me a knock-knock joke. So I'm German, background info, I moved to the US, and I'm still struggling with knock-knock jokes. So I'm asking my foundation models to come up with one. Let's say it responds with clap, clap. I mean, it's kind of funny, right? But it's not really helpful. It's not a real knock-knock joke. Also, sometimes the model might respond with something that's completely wrong, right? Can coughing effectively stop a heart attack? Of course not. But maybe the model just, assumes it is and really confidently say that. So it's not really honest in this case. And also sometimes the models can provide bad advice, or even like, how can I hack my neighbor's Wi-Fi? It definitely should not give you tips and best practices in this case. It just like stop and say, hey, I will not answer this. So it can create a little bit of harmful content. Sometimes it can be hallucinate, create misleading answers, and sometimes just not helpful. So how can we address this, right? And those 3 points, helpful, honest, and harmless, by the way, are often referred to as the 3 H's, HHH. So whenever you hear that, that's referring to those overall kind of alignment criteria. You want the model to be helpful, you want it to be honest, and you want it to be harmless. All right, and this is exactly why we're doing RLHF. We're trying to align the model with human feedback to guide it towards harmless content, honest content, and helpful content. Let's talk a little bit about reinforcement learning from human feedback and what's happening here. Usually you start with an instruction fine-tuned model. So the model that already understands how to use instructions and how to respond.
Everybody cool up to this point?
Yeah, it's great.
Okay.
Yep,
Just
good.
want to make sure that we, everybody's cool with everything. Okay.
To different tasks. And then you're applying this RLHF technique as a second fine-tuning step to align the model further across those criteria. Again, maximizing the helpfulness, the relevance, minimize any harm, and avoid the model engaging in any dangerous topics. So before we go into the details of RLHF, I just want to make sure everyone here is familiar with the terminology. If we look at classic reinforcement learning, you might have heard about the terms. We're often speaking of an agent and an environment. The goal here is to maximize the reward. So the agent will take actions in this environment, and then based on the action's effectiveness towards a goal, it receives a reward. So it takes an action, and the action will put the environment in a specific state, and I'll explain what that means with an example in a bit. And then based on how good that action was and the resulting state towards the end goal, there's a reward. And it's much easier to understand if we use an example. Let's say we want to play tic-tac-toe. The agent would be the player. And the objective here is clearly, hey, I want to win the game. The environment here is our 3x3 board where we play the tic-tac-toe. And the state is the configuration of the board at any step we're taking. And the action space is the allowed moves I can do. So wherever I can put my X or put my circle here. So how the agent figures out the best way to win this game is by using what we call a policy, a reinforcement learning policy, which is often a model that learns what actions lead towards winning the game efficiently. And based on all this input, like what's the state given the action I've taken and what's the reward, the policy will evolve over many iterations and figure out actually by learning, right, trial and error, which one is the right policy and the right strategy to win the game. And a whole play out like here, like I do the whole iterations until I win or lose the game is called a play out, or if we're talking about language models, often called a rollout as well. So we're not playing tic-tac-toe, unfortunately. We want to fine-tune large language models, which is also fun. So how does this concept here apply in the context of LLMs? So we still have an agent and an environment, but in this case here, the reinforcement learning policy is our instruct fine-tuned model. And the objective here is not to win a game, but to generate text.
Are you guys familiar with this Instruct LLM model? It's a stripped down version of GPT-3, I believe, that they used in their training. So when she says that, you can almost use GPT-3 interchangeably with this model if you're not familiar with it. Okay.
And we want to generate the text in an aligned fashion. So what we discussed before, if we want to align for the helpfulness, that's our goal here. The environment is the context that the LLM has. And the current state is the current context, meaning whatever is in the context window right now, plus the generated text until to this point. And then if you wonder what are the actions, well, the actions is literally taking the token vocabulary as my action space, the total amount of possible actions, and then generating token by token. And this will give a reward, and we'll walk you through how this looks like, and then informs the policy here, how to adjust the model to make more aligned responses. And this is where the human comes into play. So somebody has to say, is this text really better? Is this text really more helpful, right? And usually this is done with humans. At scale, this doesn't really work anymore. So we don't want to have like our colleagues or you yourself sitting down after every model completion and evaluate the text, right? So this is why we're training a reward model that takes this place. It's trained based off the human feedback, so it basically incorporates that knowledge, what you would prefer. But then the model can make that call in the RLHF process and assign a reward score to those completions. All right, and the whole thing is called, in this case, a rollout. And we're going to talk a little bit more about the reward model here, which is super interesting to know. And I saw a lot of questions also submitted beforehand. You want to understand a little bit more about the algorithms and the reward models, so let's talk about that. All of it starts with, first of all, collecting the human feedback.
Okay, are we okay up to this point? Everybody's just following along, right?
Yep.
Okay.
Yep.
So how do you prepare this data set to train the reward model? Let's start with our instruction fine-tuned LLM. And usually what you can use is either you have your own data set or you can use any of the publicly available prompt data sets. And then you will take a couple of samples, prompt samples, and you create model completions. And you'll create like a couple of those. Like here, for example, let's create 3 different completions for the same input prompt. And you do that with a couple of different prompts and always get a couple of those. And then you need to know what you want to align for. So let's say you want to reduce the toxicity or you want to improve the helpfulness, etc. So you select one, and then you're providing instructions to a group of human labelers to then provide the feedback and basically rank the responses. So let's say we have a prompt, my house is too hot. You run it through the model. And there's different completions. So maybe the first one says, there's nothing you can do about hot houses. Nah, not really helpful. Or you can cool your house with air conditioning. Yeah, that makes sense. Or it is not too hot, which is kind of a weird response, right? So let's say we want to hear a line for really the helpfulness of the responses. You have a group of human labelers, and their task is to rank the responses. 1 being the most helpful, 2, 3 in this case being the least helpful. So in this case, I think we can all agree air conditioning is a great tip, so most helpful. There's nothing you can do. Nah, not really helpful, but it's better than the third response where it says like the house is not too hot, basically saying my whole statement here was wrong from the beginning. And you're not just doing one human labeler, you usually send those completions to different labelers to get some diverse input, to find consensus here also in the responses and the ranking. And sometimes, you know, a labeler might just misread the instructions. And you can see here that there's a little difference in the rating. So if you send it to more than one, you can find that, catch that, and minimize kind of the error rate here and find a good rating. All right. It's important that you provide good instructions. Here's just a couple of examples. I'm not going through all of them, but provide instructions that are really clear to make sure, you know, increase the quality of this data set. And
Hello? Somebody say something?
What is it? You're calling from where?
Calling from other home garden. Okay.
Sounds like somebody's on a phone or something. Okay,
Okay.
maybe.
He's muted. Go ahead.
Okay, thank you.
The labelers know exactly what they should do. Like tell them really rank the responses here from the best answer to the least helpful. You can also give them tips like, hey, judge on the correctness of the answer, the informativeness, and also they could ask, for example, check the internet, search the web to make sure it's correct. And then also they can kind of, if they don't have a clear winner, they may rank the answers the same, but they should only use this kind of sparingly. So again, here you can give all of the instructions you want to do and make sure the human labelers know exactly how they should rank it. All right, let's say we have this ranking data now, sometimes also called the preference data set. And to prepare it now for the reward model training, we need to do a little bit of data engineering here. So we have the prompt and the completions. We also have kind of the average, like the rank that we agreed on. What we now need to do is to create pairwise completions. So you can see here that I'm ordering, if you can see the colors, purple, yellow, green, yellow, green. So all the possible combinations. And I also have the reward. I know from the ranking which one was the preferred from each of those two. One little weird thing that most of those algorithms do is they require the preferred answer to come first. So if you see what I'm doing here in the last step, I'm switching the order. I'm putting the yellow box first, the yellow completion, because that was actually the preferred one. So that's just like a detail.
Has anybody ever seen that? When I was doing this stuff with Bard, I didn't have that requirement. And I was wondering if it's just maybe Bard is just kind of the weird ones that doesn't, or does anybody ever heard of having to push that to the front before?
Maybe it is doing it implicitly behind the scenes. Once you rank them 0, 1, before they start sending the data for training for the model, right? The reward model, they may implicitly be doing it.
Well, yeah, I guess that kind of makes sense because they probably don't want to see too much variance from the first one. Kind of, kind of locks everything. Doesn't lock everything down, but it, kind of sits in there. So maybe that's it. Okay.
That many of the algorithms that implement RLHF expect you to do. So make sure you check for that and then always pass in the preferred one first. All right, now we've prepared the data set and we can train our reward model. Let's have a look. So again, the reward model will assign the rewards later during the RLHF process, and it needs to capture the human preferences so we can scale it and don't need the human labelers in every step here. So what we're doing is we're getting the prompt and completion pairs. And again, the first one here is the preferred one. And then we're passing in the second option. And we're training the reward model here to predict the preferred one. And it's the usual loss calculation here because we know which one it is. And then for normal backpropagation, we update the model so it can always predict which one is the preferred one. And again, here we're feeding in the preferred one first, just a quick reminder. So once we do that, and basically you can guess picking 1 out of 2 sounds pretty much like a binary classification problem, right? So this is exactly what we do here. So for example, if we're looking for reducing the toxicity, what we could do is kind of use the reward model then to say which one is the preferred, the positive, right? Is it positive, is it negative? And we want to optimize for positive to reduce toxicity, which we'll also use, by the way, in the hands-on part here in a little bit. So when we're using the reward model now, we can feed new prompt completion pairs. And if we're using this as a binary classifier that has been trained to exactly distinguish between positive and negative, we can see here, for example, Tommy loves television, positive comes back, and with the logits, which is the model outputs before we apply any softmax layer, you can see here it's definitely positive here, no hate speech in this. And this logit value is what we use later on as the reward value. You can also see probabilities here. That's pretty much 99% positive. If we now run like a bad text, like definitely negative, you can see here that the positive class is way down, 33%, and the negative class here correctly identified, 66%. Again, for the rewards, we'll always use the logit value, and here we can see what we're trying to optimize for. The positive is a negative logit. So this will be kind of, thinking of reward terms, a penalty, right? It's a low reward. It's actually a negative reward. So we're discouraging the model later to produce output like this. All right. So this was a quick walkthrough just to understand how to prepare the data.
Somebody say something?
Yeah, I just was real quick. I don't know if maybe I missed it, but did they talk about how the reward model is initialized?
I don't think I saw anything in this lecture that does that.
I
Okay.
thought you said just start with any pre-trained model. It didn't really matter. I thought
Just
yeah.
a foundation model, meaning?
Yeah, like Instruct GPT is a, like I said, a version of GPT-3 that has been a little bit tweaked for this purpose. But the assumption, yeah, I think Sally's right. I guess the assumption is you have a foundation model that you can start with. If that,
Okay.
Does that answer your question, Roger?
Yeah, that was totally it. Like, how do you learn the reward function, basically? And I would have thought that's important, but
Yeah.
I mean, if I start with GPT, 2 versus GPT-4, there's going to be a big difference, I would think, on how well this performs.
Yeah.
I thought the reward function is not learned here, right? So the rewards are explicitly coded up by virtue of the person who has given those rankings. So let's say there are 5 responses each time. Mm-hmm. So in the trajectory that evolves in the RL, you have, every time, like at every time step, you would have like, it's the 4th one, or it's the 3rd one. So that is your model.
Well, that's the training data.
Right.
The training data goes into a model, and what she's creating right now, I believe, if I understood the architecture she's describing, is she's creating a model to generate the reward.
Oh, so why do you have to use, so to do that, you don't have to use a NLP foundation model at all, right?
Well, because they're trying to do a fast train, it sounds like, on a natural language response. The association between the natural language response and the reward, which if you go back, Jerry, 10 seconds here, that table that she presented, that's effectively your objective function for, this right here,
right,
for the reward model.
So the input to the reward model is a text prompt and a text completion. And that's why using a foundation model as the starting point for the reward model makes sense.
It kind of feels a little bit like like we're moving towards a GAN, but like it's kind of a hacked together step-by-step manual intervention, how to build a GAN from scratch.
You have to wonder if when they first tried that, they tried to just fully automate this and ended up with the garbage and then said, "Whoa, well, we need something that
that's frequently what they do, right?" And then you add structure, right? And try to figure out a way
and
to
the structure was, we'll hire a bunch of people to classify this stuff, things like that, which is okay. That's one way to do the problem.
Well, and then we eventually learned how to generalize, right? Because generalizing, you have to figure out the dimensions and the methodologies for generalizing.
Yeah.
So in essence, what you end up with is a language model that's been tuned on a very narrow task, which is better, positive or negative. And that's then able to guide the other language model that we're trying to train, right? We're trying to
so the
fine-tune.
space of which the reward model is very limited, whereas a generative model has infinite space.
Yeah.
So exactly.
It's easier to say it's good or bad than to actually generate it.
And this would be specifically more useful in a chat context. And that's what I've noticed with all this buzz about ChatGPT. they overemphasize the chat aspect. So with respect to a chatting application of NLP, certainly this way of creating a reward model would be helpful, right? But it would not mean that you would have a application for, say, relation extraction or something else, which would.
Right.
Yeah, the example she opened up with was creating a knock-knock joke.
Yeah.
I missed that. So I came in, I couldn't find the link. So
Yeah, we apologize for that. There was a little screw up this evening, so that we had to.
but I see
pivot.
that YouTube, there is a video recording. I'll watch it later.
Yeah. You know, yeah, there definitely will be a video recording, and everything we're saying here will be on it. But yeah, anyway, so as I think Sally was pointing out there, this is all, you're correct in your assumption that this is kind of narrowly focused on that kind of ChatGPT-ish conversational type sort of thing. It is, you know, not particularly applicable outside of that space. I don't believe, maybe somebody else knows if it is. It was purposely done this way. And that has good and bad things about it. One of the bad things that has occurred is the cost of this is very extreme, because now you have all these human classifiers, subcontractors, you know, that you have to pay out to kind of put kind of the human feedback into this scenario. So,
but I believe that this RLHF, or that human element, is what has made the chat responses from ChatGPT so you know, so effective. I guess that the world is raving over it. Right?
Yeah, you're absolutely
for years, but only with the advent of RLHF last year, suddenly this whole communication with this machine looks so good.
Right. It moved it up, you know, orders of magnitude in terms of I don't know what you want to what metric you want to use, but in terms of acceptability and, you know, the amazement people have and whatever else has now come after ChatGPT has appeared, fear, whatever you want to call it. So, but yeah, you're absolutely right. You're absolutely right. That has.
I'm wondering if this is, so this RLHF kind of trains it on how to kind of carry on a dialogue, right, between two participants. So it's not just repeating the textbook, it's actually learning how to, if a question's asked, how do I respond to it, type of thing.
And in a sequence, and continue that in a sequence.
Yeah.
Yeah.
And I would think that there's some examples of that in these data sets that they're drawing upon. Things like Stack Overflow would have been kind of like that. But you know, I wonder if maybe it's just a matter of the quality of that dialogue in their other data sources just wasn't high enough, and this is a higher quality source of dialogue information.
Yeah, that's a good question, Roger, and I don't know the answer to that, but I think you're on to something. You know, I did this thing I mentioned for Bard as part of the GD program, and they gave us very, very explicit instructions, like pages over them. When you're putting in your responses, we want them to kind of look like this. You know, if the question was like this, you should really respond something like this. You know, so it is definitely an engineered, a restricted, engineered, whatever you want to call it, you know, format that you're putting them in it. So,
yeah.
Well, and I think it's an interesting question, because I think when we had the very, very first couple papers on GPT models and attention models, they made the academic paper made the assumption that it doesn't matter whether it's a question and an answer or the second half of a paragraph. What we're doing is we're completing something. And I think that to Roger's point, the data set on which that's trained, which we kind of consider the broader universe of data, is not as highly focused on point counterpoint dialogue. And so while academically that point held, from a bias in the data used to train perspective, I think we're essentially trying to compensate for that. And it sounds like with this, the RLHF specifically, is we're trying to compensate for that in some sort of a reinforcement learning context.
Yes, we're trying to get the reinforcement learning to compensate for that, I think is the bottom line on that. So, all right, I'm going to move forward here.
Let's do it.
66%.
Oh, I guess.
Again, for the rewards, we'll always use the logit value. And here we can see what we're trying to optimize for. The positive is a negative logit. So this will be kind of thinking of reward terms, a penalty, right? It's a low reward. It's actually a negative reward. So we're discouraging the model later to produce output like this. All right. So this was a quick walkthrough just to understand how to prepare the data. Now let's jump into the actual RLHF fine-tuning. We start with our instruct model, and this is the model we want to align. So this is getting updated. Again, we have a prompt data set, either your own one that you created, or you use one that is existing. And for example, here an input might be a dog is, and the model comes back a furry animal. You then pass prompt and completion into the reward model. And the reward model is trained to give you this reward value, which is the logit value that I just showed you. So in this case, it's not too bad, right? It's definitely not a toxic response. Is it helpful? Yeah, it's okay. But maybe you want to align it for a little bit more, you know, positive speech. So the reward value is okay. And what's happening now, the prompt, the completion, and this reward is passed to the reinforcement learning algorithm that you're using. And I'm going to touch on that a little bit later. A popular one is called PPO. And the reinforcement learning algorithm will now, based on the reward, update the model and say, yeah, it was good, but you probably can do better, right? So you're doing a lot of iterations here. And maybe the next one, let's just go ahead, responds a friendly animal, which is slightly better. So the reward might go up. The next one might be a human companion, which I like. Yeah, so reward goes up. And the most popular pet sounds nice. And you get the idea, right? So I'm doing a lot of iterations. The goal is to maximize this reward score. And maybe here iteration and the last one I'm doing, because I have a stopping criteria, maybe number of steps. The completion comes back, a dog is man's best friend, which sounds really nice. And this is going to be then my human aligned model at the end of those iterations. All right, let's zoom in a little bit more on the RL algorithm part here.
Was everybody okay with that before we go into the PPO stuff? So they just went through.
I got that part.
Yeah. Okay. Cool.
The only thing I noticed is, so originally they were saying the instruct GPT is the one that's doing the generation. And again, they didn't really dive into what was inside the reward model, right?
Yeah.
But we're saying that would be some language model.
Yeah. Yeah.
Okay. Thanks.
Yeah. Don't know how to better phrase that.
I think the reward model, as it was shown a couple of slides back, is just one fixed prompt, and you know, everything else is like you know, the 4 or 5 human choices for various prompts. That's all. So it's not very full-featured foundation LLM.
No, I mean, yeah, the report part is probably separate from the actual LLM itself. It's, you know, it's a human engineered type thing.
Yeah, and now that I'm looking at this picture, the reward model circle just is a way to generate a numeric value.
Yes,
that's all.
So Mike, that's a regression head versus a generation head. So the underlying model, like the hidden nodes or the structure, underneath that could be very simple, or it could be very big. I think the question is just really, what did the paper specify what that was? And I did not hear her specify specifically the architecture that goes in there.
Yeah. Right. Okay, I'm going to move along here.
Thank you, Jerry.
I mentioned before, you can pick your algorithm. A really popular one being used in RLHF implementations right now is PPO. PPO stands for Proximal Policy Optimization. In the course, we have a whole optional bonus section where we're diving a little bit deeper into how PPO works. It's a whole world in itself. So for today, I'm just going to give you a high-level overview and description here. But if you're really curious to learn more, diving into the different loss functions, how the clipping works, I definitely recommend enrolling in the class and checking that video out. Here today, I just want to give you a high-level overview. So PPO uses 2 stages. In the first stage, it uses the model that we have at this current step, whichever we're in, and creates a couple of prompt completions. It's called experiments. And then it calculates the rewards for those. And in the second step, it then updates the model based on the average, the rewards, right? Like if it's not a good reward, it feeds it back propagation, and then updates. And there's a lot more complexity to that. There is terms around the actual policy loss that's getting calculated. There's a value loss. There's an entropy loss. So if you're interested in that, I strongly recommend looking into the course. For today, I want to keep it at this level to kind of get through the whole concepts and also get to the hands-on part. All right, is that all? You might think that wasn't too bad, right? Well, there's a little bit more I want to touch on, a little bit more complexity. So if you think about how this works, one of the potential problems here could be reward hacking. So what does that mean? Let's say we have our model that we want to align, and we have this reward model. Let's say it's a toxicity sentiment classifier. It knows positive, negative. And we're passing in the prompt data set again. Maybe here, this product is complete garbage. Okay, that's a negative reward. That's nothing we want to say. PPO comes into place, updates the model, boom. It learns that it has to be more positive. Okay, so maybe the next one says, okay, but not the best product, which is better. But now it spirals out of control. What if the policy now learns, hey, the more positive terms I'm using, the higher the reward? Remember, in reinforcement learning, the goal is to maximize this reward. So this might be just, okay, I learned that positive token respond to high rewards. So maybe here completion comes back, the product is the most awesome, most incredible thing ever. It's definitely positive, but I don't think we want to produce that, right? And then maybe even getting worse and saying beautiful love and world peace all around, which has nothing to do with my actual prompt anymore, right? It's just going off the limits, producing really nice sounding crazy words here, but you see the reward goes up, but it's not what we want the model to do, right? So this is kind of called reward hacking. How can we avoid this? The way we do this is by keeping the updates in check. We're using the initial model, which wasn't too bad, right? We might just want to align it a little bit further, but it was good in creating the output at its core that we want. So we take the instruct model, the initial ones we had, and we're using this as a reference model. And we freeze the weights. So this model is not getting updated. It's just our checkpoint, our reference to make sure there's no reward hacking happening in the one we update. And we're feeding now the prompts to both models. And again, the reference model will have like a very neutral response, most likely. And then the one we're updating will do whatever it does. And we're using now a metric called KL divergence. You might have heard of that. It's a statistical measure that calculates the difference between 2 distributions. In this case, it's our token vocabulary distributions that the model learns. And we're calculating this divergence. And what's happening is, here it's getting a little bit complicated, but it's added as a term to the reward calculation. What that means is, in case the model goes off and creates world peace in every completion, it's diverging from the initial token distribution, right? And this will be a penalty term. So this gets added to the reward score before it goes into RLHF. So by adding this as kind of a penalty term, it keeps the optimization in check and says, okay, this was bad what I was doing here because I just got like, negatively affect on my reward. And we'll see this also in the hands-on here in a bit. Now,
So Jerry, this seems like
there's
a hack.
another thing, and
Yeah, I would agree. It seems like, right, they got in there and this thing kind of went off into Never Never Land and said,
But
oh
I mean,
my
that's what
God.
reinforcement learning is supposed to do, right? Like, so it almost seems like, I don't know.
Well, Sally, I mean, the PPO has that KL divergence in it, doesn't it?
Yes,
Well,
and
she's
that's
describing the PPO algorithm. It's like
yeah,
policy. What is it? Policy
proximal
policy.
policy
optimization.
optimization.
Yeah.
Yeah.
So you want to keep it close, but improve one metric.
Yeah, and if I remember right, you know, the way I think we've talked about this, gosh,
Yeah.
what, couple,
Yeah.
2-3 years ago or something like that now?
Yeah.
Yeah. And if I remember the way that worked, you could envision it like you were walking down like the top of a very steep hill that fell off on the left and right. What you didn't want to do is take that sharp turn to the right or sharp turn to the left and essentially fall off. You just wanted to do, well, let's just, you know, move half a foot to the left and see if that works better. Or move a half a foot to the right. Not, but you know what I mean? Just, it was sort of putting, I don't know, boundaries or, you know, preventing massive shifts in direction on that. If, you know, if I remember how that works.
Kind of like improve the reward, but don't blow at everything else that you do.
Yeah, exactly.
Yeah.
Or improve it, I won't say slowly, but consistently. Maybe that's a better way to say it.
Well, I mean, the interesting thing about doing it with a frozen model is that in a sense, the speed matters kind of, but it's the ultimate distribution that ends up mattering, regardless of whether you got that distribution quickly or slowly. It's just, I don't know, whatever, that's fine. If it's part of PPO, then it's part of PPO.
It seems like
it stabilizes the training, I think, fundamentally.
Yeah. They'll go into it a little bit. Well, they'll go into it in a minute about other things they can do.
I mean, it's just interesting in that, like, RL is designed to go as far in a direction as possible. Like, that's what RL's supposed to do, right? And so, I don't know. Again, as a lover of, you know, RL in its purest form, makes me sad. It's okay.
This is a class of algorithms called actor critic, and I've just looked up the paper. I have it up open. It seems like it was invented by OpenAI company in August 2017. So it's their own invention.
Yeah, and not surprising they use it then, right?
Well, I think, didn't PPO become very popular? I mean, it was one of the ones that was really kind of being used most often, I thought.
Yeah, no, it is. PPO is because of it. It has that ability to not walk off the edge of the mountain type thing,
right?
You know, and going so far that you do that, if I remember right. But yeah, but it is. If I remember, but PPO is is it the other point is an OpenAI algorithm, right?
Yeah, and also it is okay. So I took a course on reinforcement learning, and we didn't get to this actor critic class of algorithms because you start out and you learn those algorithms like reinforce, REIN in all caps, and etc. So I think this is a newer class of algorithms, and maybe that's the reason you have the critic part of the, which is other piece.
Yeah. All right. I'm going to move on then.
This might get a little bit complex here as well, but there's one optimization I just want to point out, and we talk about this in much more detail in the course. Those models can get really big, right? I mean, we're talking billions of parameters.
So Roger, this is for you.
Sometimes 70 billion parameters, etc. So fine-tuning a model and updating all of its parameters, it's really kind of a resource-intensive task, time-consuming, etc. So what you can do is you can optimize this with a technique called parameter efficient fine-tuning. And it reduces the number of parameters we're actually updating in the model to a minimum. And one technique uses adapters, which I'm going to show you just briefly in a second here. So that means combining the PEFT methods, for those of you who have heard about those already, with RLHF is super helpful in making this more efficient, because in the RLHF cycles, you're only updating this small amount of parameters and keep the base model, again here, frozen. So super helpful to do this.
So Roger, was that correct in her description?
Yeah, it totally makes sense. Totally. Yeah.
Okay.
And usually the PEFT models can then be fused into the primary model afterwards if you want.
Oh, did not know
So
that.
it's just kind of a training optimization.
Yeah, I think you discussed this like 3 weeks ago or something like that. So I thought it was
The PEF stuff,
interesting
yep.
that it kind of came back around here. And so I thought I'd give you a shout out.
For those of you who haven't heard about PEFT, just a brief intro here. Parameter efficient fine-tuning, there's a couple of different methods. The most popular one here in the middle is called LoRA, low rank adaptation of language models. And I'm going to show you what this does. But there's also different ones. You might have heard about soft prompts and prompt tuning, but we're going to focus here today on LoRA. LoRA, what it does is it freezes most of the overall original LLM weights. And then in the attention layer of our model architecture, transformer-based architecture, it injects 2 lower rank decomposition matrices, which are way smaller than the original matrices that are used here in the attention layers. And this goes into really kind of the architecture of the model. But overall, we're learning only to update those smaller amounts of parameters that I have in those matrices. And this helps to make this whole fine-tuning, and in this case, fine-tuning using RLHF, way more efficient.
So Roger, did she get that right on that?
Yeah, sounded right to me.
Okay. Just wanted to make sure.
PEFT is pretty much like quantization, right? You're doing like.
Yeah, no, actually, I think those are separate. Sometimes they're combined. We went over QLoRA, which did quantization and low rank adapters, but they're 2 separate things. In one case, think of it as kind of adding matrices in parallel with either the attention or the MLP layers, and you train them. You freeze the original, and you train these new, small number of parameters to augment the original, so you can, achieve whatever your goal is. That's what these adapters are. Quantization is just a way of reducing the memory footprint of the parameters at large. In the QLoRA that we read, they quantized and froze the model, and then they use low rank adapters to tune the model.
Okay, thanks.
Does that make sense?
Yeah, because they kind of, if I remember right, they kind of use both of them together, right? In that.
Yes, correct. Yep.
Okay. All right.
And the low rank adapters, just again, if I'm going to summarize it into one sentence, it's essentially modifying only the parameters, not modifying, that's not the right term, affecting the flow of information through the parameters that actually matter for the unique objective that you've created. So you're not modifying the entirety of the model. You're only modifying. If it were only one, it would be something like PCA, essentially. Is that right? That you're kind of focusing your attention on the parameters and the flows through those parameters that differentiate or discriminate on the dimensions that you're interested in.
Yeah, I think that's fair. They do it different ways. Sometimes it's in line with the original model. Sometimes the one that's most popular now, I think, the LoRA, is in parallel. So they have just a parallel matrix multiply. And the
so you're not touching the parameters, you're touching the outputs of those parameters.
Yes, right. It goes around. Yep. But it has the same effect. Yep.
Okay. All right, I'm going to continue.
All right, and we're almost ready to jump into the hands-on part for today. So just to wrap this up, once you're doing RLHF, you also need to evaluate how effective it is, right? So what you can do is you're going to calculate, which Chris will show us here in a second, so get the labs ready, by calculating a score. In this case, we're going to show you how to try to reduce the toxicity in outputs, and to show the evaluation, we're calculating a toxicity score. So we have a data set, we're running prompts, completions, and then the score is the average probability of the negative class across all of those completions. So that should definitely go down. So the lower toxicity score, the better. And there might be different ones coming out. So maybe you run this before you start RLHF and you come at a 0.14 score. And after doing RLHF, you might recalculate this and come out at a 0.09. So the toxicity score went down in this example, and you know the RLHF worked. And you can also obviously do a qualitative check where you're actually looking into the completions and make sure that it produces the right results that you are looking for. All right, I know this was a lot. I just want to make sure everyone is kind of on the same page, has heard the terms before, and now I'll hand it over to Chris.
Okay, I'm going to actually stop at this point because we only have 9 minutes left. Questions, comments, things like that? Learn something hopefully you didn't know before, that sort of thing.
No, nice job. Thank you for taking us through that.
Yeah.
I
Yeah,
did want to take a second, since we have a bunch of people that weren't on at the beginning, to talk about next week and participation. Roger sent out.
Let me stop sharing the screen then, if that's okay. Okay.
And we probably stop. Well, we can keep recording. Doesn't really matter. Roger stuck in the comments there the Slack channel, if anyone's interested in joining the Slack channel, which is where we do kind of more of the real-time announcements, like, hey, our Zoom didn't work. Zoom will be fixed next week. So I took care of that while Jerry was doing the presentation. And then next week, I'm going to try to present something kind of along those same lines of Laura, what she was talking about, which is a paper that has a very dramatic claim, which is to be able to do like a 100 kilobyte model that does text to speech. And to again quote their own synopsis, it's only 5 orders of magnitude better than the current state of the art. So it's like it's room temperature superconductivity made with household materials, right? Like, I mean, you're just going in your laundry room, you're getting out some bleach, some soap, and you're getting superconductors out of this thing. It is awesome. So I don't know. We'll see if it ends up being complete BS. Nonetheless, it's in archive. It says it was reviewed, so it'll be interesting to watch.
What's the name of the paper? What's the name?
It's so it's in the agenda. If you join Slack, it is called Key Locked Rank 1 Editing for Text to Image Personalization. This allows runtime efficient balancing of visual fidelity and text alignment with a single 100 kilobyte trained model, which is 5 orders of magnitude smaller than the current state of the art. So I don't know. We'll see. But that's what's next week. So I'll be presenting my first paper in almost a year now. So excited to do that and kind of get back on the horse. And then after that, the following week, we have Dave will be doing score-based generative models. On the 31st, Shulin will be doing simulation-based inference. And then the 7th and 14th are open for next month. So if anybody's interested in presenting something, Mike, you mentioned you took a class. If you have something you want to present from that, or anybody, right? Like, this is a group where we want to have as many beginners participating in all levels. If you want to present a paper where you would like help, where you're going to do the reading and you want somebody to do it with you, we do co-presentations as well. It's just a really neat opportunity to learn. Everybody gets a chance. I think that's all I really wanted to jump in. And then Dev is taking over the 21st of September, but we do have a couple slots open.
I'm looking in the Slack channel. Where is this paper?
So the Slack channel is at the very beginning of Roger's. Roger, you sent that out, right?
I sent the link for joining Slack, and the channel is the agenda channel.
And then the spreadsheet with the agenda is in the agenda channel.
The description of, yeah.
And, as many people as we can. Tell your friends.
Tell your friend. And tell your friends if they want to present something, they're welcome to.
Yeah. And, I think to reinforce what Sully said too, we have people all up and down different levels and things like that. We're all on different journeys. And with machine learning and AI, I'm like right now looking at these language models, but, other people may be looking at vision models, and there's no way anybody can do it all.
Yeah. I mean, like two and a half years ago, this guy shows up. He's been to like 10 or 20 of the meetups. And he's like, hey, I want to show this. I want to do a paper and changed the whole direction from image stuff to this thing called all you need is attention is all you need. And he shows this stupid paper. We spend like 4 weeks on it. This is Dev Vidhani, by the way, in case you're wondering. And he turns out to like catch on to the next wave, and he's the one that carried us there. It was amazing, you know. And I think we literally spent like 5 or 6 weeks just tearing apart that first paper, and I think that was one of Dave's first presentations. It was amazing. It was amazing, and it foretold the future where we went with AI. So it was neat to kind of be able to carry, you know, everybody's perspective coming from different directions. And Dave was actually even very apologetic initially when giving that presentation. Like, I know we mostly do image, but this NLP stuff's rad. So he was right.
I still am because I'm sure I made a lot of incorrect comments and statements, but
fortunately we weren't recording.
Yeah, it was mostly the
but we
rude
didn't
stuff
know
that
at that
said.
time you were wrong. You know?
Yeah.
So you're cool. It was cool because it was just so like out there, you know, and you were taking us in a great direction.
But I do want to add to what Sally said. You know, it's okay to make mistakes, and this group is probably the best forum for anyone to come and present and learn along the way, make mistakes, and you know, we all learn along the way.
Amen.
All right.
All right, guys. Thank you.
All right.
Yeah, join the Slack if you can, and otherwise we'll see you next week.
See you guys later.
All right. Thanks.
Bye.
Bye, guys.
Yeah, thanks.